Yeah, so we just started talking about Boolean circuits. And in this talk, we will talk about generic classes, which will be denoted by script C, and S of n will just denote the number of gates that can be allowed. Usually, this will be polynomially sized in the number of inputs n. So let's say that a language L has circuits that belong to some class C here. If there is some family of circuits, Cn, which are contained in this family script C, such that the circuit outputs one if and only if the string is in the language. Now that we're talking about families of circuits, there are two ways I can classify these families, and that is non-uniform versus uniform circuits. What are they? Well, a uniform circuit, you can think of it as having some kind of a generic algorithm that takes some input length n and gives the description for the output of Cn. This is something that we would commonly think of, right? Like any program that you write without a specified input length, which takes the input length as parameter, basically fits into this regime. They are uniform circuit families. But these are not the only ones to think of where the structure that is there for input length N1 and N2 have some similarities in them. You can also have circuit families where they are absolutely not related to each other in the sense that it's an arbitrary collection of circuits. And just because I know the circuit for input length 5 does not mean I can make any conclusion of what the circuit for input length 6 would look like. Now, why should we care about these uniform and non-uniform circuit families? An interesting thing that happens is that non-uniform circuit families can do some very weird things. For instance, for at least a fixed input length, you can say that, well, they actually solve the halting problem. Now, when you think of, let's say, the input as being length n, you get the string 0 to the n, and all of the strings that are there in the language essentially say that the nth Turing machine halts. Now, for let's say n, I know some structure of the circuit that can decide this, but of course for n plus 1, maybe that Turing machine does not halt. And so there is no connection between what n and n plus 1 the circuits would look like. But at every level, they can somehow decide the halting problem. So you get these weird things that happen. And in this case, the question becomes then how do we exactly relate the power of these uniform and non-uniform circuits? And one way to do that is circuit lower bounds. As with pretty much everything in complexity theory, it always boils down to resolving the P versus NP question. And this can be viewed as a combinatorial approach to trying to answer this. What does that mean? Well, I can rephrase the question slightly to say that maybe now I want to show that NP cannot be solved by any polynomially sized circuit family, whether uniform or non-uniform, right? Well, I guess we all widely believe this, and if that were the case, we can show consequences like the polynomial hierarchy collapsing and so on, but we still don't have an explicit proof for this. So if our goal is to get an explicit proof, we can always ask, well, is there an easier problem that I can solve? Maybe not polynomially sized circuit families, which could have high depth, but can I show that it cannot be solved by constant depth circuits, right? We still can't do much in this range. Maybe there are some things where you can say that certain operations don't exist in the class of monotone circuits, or that parity is not contained in like a constant depth circuit class AC0 and so on, but still not too much. So let's try and make the problem easier. Can I show that a very large complexity class cannot be solved by a very small circuit class? And one of the works that is in the flavor of the results we'll discuss here was by Fortnow and Clevins in 2009, where they showed that if some circuit class C had a pack learning algorithm that could run in polynomial time, then randomized exponential time is not in this circuit class. So you get a separation between the circuit class and like an exponential time circuit. Complexity class. Of course, that is really large, but at least it gives you the first result. In a slightly different way that was taken, some of the best concrete bounds that we can actually show right now is by Ryan Williams in 2014, when he showed that next is not contained in ACC. What are these acronyms? Next is non-deterministic exponential time complexity classes. And ACC refers to a circuit class, which are constant depth circuits. and they have and, not, or, and mod m gates for any m of your choice. So this is the best that we can do. Now, all of these results, of course, are in the classical space, and we're always more interested in getting the quantum angle here. So one thing we can think of is, well, why not just stop at P versus NP? Maybe the question that we should care about is what is the question of P versus NP versus BQP as well, right? Because any classical techniques that can be used to separate P and NP may not necessarily work for the quantum case if NP and BQP are incomparable in some sense. So then the problem becomes, can we show that quantum computations cannot be simulated by small classical circuits? Well, again, we do believe this should hold, but we're looking for a way to get an explicit proof. And our result says that if a circuit class C has what we call non-trivial quantum learning algorithms, then there is a large quantum complexity class that is not contained in this circuit class. This large complexity class is BQE, which is an exponential time analog of BQP. And that essentially is the crux of the result. The next thing I will cover is basically the quantum learning models that we are considering, because I talked about non-trivial algorithms and I need to define what those are. But if there's no questions at this time, I will proceed. Okay. So what is the model we care about? I say that there is a learning algorithm A for some circuit class C. And the goal is to learn some unknown function in the circuit class when you're given oracle access to the function. What can the learning algorithm do? It can ask for what are called random labeled examples. Here, x1 and x2 are distributed according to some fixed distribution D. And the oracle will return back both x and f of x. The algorithm can also ask for membership queries where it says, I have a specific value y1. I need you to tell me what f of y1 is. And it continues to make these queries. And at the end of the day, it outputs a hypothesis. Now, one thing I will point out that usually when we talk about quantum pack models, the hypothesis that you get out here is usually also a classical description. In our case, we say that we want a quantum hypothesis U. And you can think of it as being needed for two reasons. One is for the proof to go through, we need all of them to have some kind of a quantum black box structure. And so we want a unitary description that can be bootstrapped into further steps of the proof. So for that reason, it helps. But the second reason is that obviously a quantum hypothesis is more powerful than a classical one. So in some sense, we're looking at a stronger model. And the intuition is that that should probably help us get easier lower bounds. So that in that case, it helps as well. What is the condition for this hypothesis to satisfy? I should say that it has to be close to this function you want to learn. What does that mean? Essentially, I say that if I take an input x and I run the unitary u, and I measure the first qubit, I need it to be equal to f of x with high probability, which means the probability of making an error is very low. Okay, probably that should be at least 1 minus epsilon there, and it's not less than equal to epsilon. We want this to be high, to happen with high probability. So sorry about that. Okay, so I say that a learner is an epsilon learner for this circuit class C under a specific distribution D. If for every function that is there in the circuit class, I can output some unitary hypothesis such that with high probability, unitary is a good hypothesis. So this fits our pack model, except that now we have a quantum hypothesis in the picture. Two things to bring up here is what are these trivial learners here? You can do the obvious thing where you just query the full truth table of f for every x, and in that case you would make no error. You would learn the function completely, and in that case, you basically have learned it completely. The second thing that you can do when you get a quantum hypothesis is that I can do Fourier sampling. Essentially, my circuit, the hypothesis that I get, does the Fourier transform. I just measure it in the Fourier basis and get one of the basis elements. And I can either output the characteristic of that element that I receive, or negate the characteristic and output it with probability half. Now, this process can run in polynomial time, but it can also make some amount of error. For instance, here you get error half minus omega of 1 over 2 to the minus n over 2. So it's not perfect, of course, and it doesn't do much better than random, but it is runs significantly faster than exponential time. And as far as we care about in this work, we will call these two things as the trivial learners, which means anything that does not satisfy either of these parameter sets will be a non-trivial learner. Before moving on to the main result, any questions at this time?
Yeah, Aarthi, what was that Fourier sampling learning?
So Rahul, essentially what I'm going to do is just do a Fourier basis or Fourier transform on the function, and I measure in the Fourier basis. So with some probability, I'm going to get, let's say, one of the sets that gives me a basis element of the Fourier basis, right? Because with probability f hat of s square, I'm going to get some s.
Okay,
And
so you're learning the Fourier coefficients, you mean?
yes, you learn one of the Fourier coefficients, and the answer that I will output is that with probability half, I either output -1 to the x dot s, or I output -1 to the x dot s plus 1. And that is going to be my answer for this hypothesis.
Sorry, okay, so I'm just trying to understand.
Yeah.
So you want to learn, you want to for a given some new x, you want to output f of x, right?
Yes, so I am going to be given a random x as the input, and I want my algorithm to predict f of x.
Correct. So what's the plan? You will learn one Fourier coefficient.
I will learn one Fourier coefficient. And once I learn that Fourier coefficient, I'm either going to output -1 raised to x dot s. So either the character, chi s basically, or I'm going to output the negation of chi s.
No, so I don't understand. Then how is it helping you to output f of x?
It doesn't. I'm not saying you output f of x with high probability. I just say that you have a little better than random chance of being good with f of x. So
Very tiny. Oh, very
very
tiny
tiny,
away from half.
very tiny away from half. It's bounded away from half, but not by much. But this is something you can still do in polynomial time with the quantum hypothesis.
Okay. All right. Okay.
That is the only claim that we're making. Yeah.
Thanks. Okay. Thanks.
Sure. Okay, if there's no more questions, I'll move on. So now that all the pieces are pretty much there, I can at least state the main result. The theorem states that if there is this class C of polynomial size circuits, it can be learned under the uniform distribution and membership query. So this is precisely the model I described earlier. And let's say that it has an error that is at most half minus gamma. And let's say the time for this learning algorithm is gamma squared times 2 to the n over n. If these conditions hold, then I can show that BQE, which is essentially 2 to the O of n quantum time, is not contained in the class C. We want some nice behavior for C, and I say that it's closed under restrictions. By that, I mean that if I fix some of the input bits to 0 or 1, I hard code some of it, then the remaining problem can still be solved in the same circuit class. So it's just a nicely behaved class. That's the intuition to take away. So what is the interpretation of this result? Because this can look very opaque. So there are two interesting sets of parameters. I can take the case where gamma is a constant like 0.49, in which case the time that I will get would be something like 2 to the n over n. There's another set of parameter I can take where gamma of n is this weird expression, something super polynomial in n times 2 to the minus n over 2. And that essentially will give me a time that is super polynomial in n. Why these two parameters are interesting for us to consider? Well, if we go back to what we discussed about the trivial learners, what this tells us is the first case is faster than just a brute force type algorithm. And the second case is just a little more accurate than Fourier sampling, because the error that you would get is not going to be 2 to the minus n over 2, but something with a super polynomial factor attached to it. So if you have any learning algorithm for this specific circuit class that does even a little better than these trivial algorithms, then essentially we can get a circuit lower bound out of it. One direct application of this, just to maybe get everyone comfortable with the result, is that in sort of previous work with Alex and Srinivasan, which showed that there are no polynomial time quantum learners for the class AC0, which is like a constant depth circuit. It has only AND, NOT, and OR gates, but they can have unlimited fan-in. But these are only polynomial time learners, and this theorem essentially can take even learners of beyond polynomial time, right? So the question asks, okay, are there super polynomial time learners? And yes, we know that there exists some kind of a quasi-polynomial time algorithm to learn AC0. This is a classical algorithm by Lineal Mansour and Nissan. And if we just plug that back in, because clearly a classical algorithm can also be converted to a quantum one, we immediately get a bound that says that BQE is not in AC0. Of course, this is not very interesting because, this is implied because of a classical algorithm. So let's say the more interesting question now that we can pose is, are there any non-trivial quantum learners for, let's say, a larger circuit class like ACC, which we saw earlier, or even depth to threshold circuits, which are essentially like a restricted, which are a discretized version of certain neural networks and so on. So it's an interesting class to think about. And also, we don't know any good classical algorithms for these classes. And so maybe if you want to show something about quantum being more powerful, you want to look for quantum learners that are non-trivial for these classes. And in that case, you would get a new lower bound that is not implied by classical results. So that would be interesting as well. As with most things in life, so I would say that this result also has two ways to look at it. If you're feeling a little optimistic today, then you may feel happy that this is giving us new ways to obtain circuit lower bounds for quantum circuit classes, quantum complexity classes, and maybe we can use these techniques to improve these ideas even more. But if you're feeling more pessimistic, then you can say that, well, it's very hard to get these circuit lower bounds. We know that because people have been trying to get them for a while. Maybe this is evidence that it's also going to be very hard for us to find non-trivial quantum learning algorithms, which is what we want to prove that quantum algorithms are more powerful. So you can take it whichever way you feel like. But yeah, that's the interpretation I would say for the result. Any questions at this time before I go to the proof overview? Okay. So let's maybe get into the roadmap of how do we go about proving this result. There are essentially 3 steps that we use to get the theorem. The first step says that if you have a quantum learning algorithm, that implies what's called a quantum natural property. I will define what this is as we go ahead, but intuitively what we should think of here is that if I can learn this class C, then then there is a way for me to distinguish this class from random functions. So think of the natural property as being an algorithm or some kind of a combinatorial thing that lets me distinguish some structure that is there in C from being completely random. The second step that we need is we assume that the class P space is, let's say, hard for some quantum complexity class. And if that is the case, then we can show that there exists a pseudo-random generator, that's what a PRG is, that is secure against uniform quantum computations. And this construction goes as follows. It has essentially about 3 or 4 steps. I start with a P-space complete language that was basically constructed by Jaiswal and Vardhan in 2007. This language may be, mildly hard. It's not too hard for us, so it may not be interesting to get a PRG out of it. So first we want to somehow amplify the hardness of this language so that you can maybe extract more randomness out of it. And we do that using a result of Impagliazzo et al. And Goldreich and Levin. So the Goldreich-Levin result can be thought of from the cryptographic sense as working on what is known as a hardcore bit, for people familiar with the concept. And the Impagliazzo et al. Result essentially tries to amplify the hardness using ideas from coding theory and local list decoding. I will not have time to go through any of the details of this result, but this definitely is where a lot of the technical meat of our work is hiding. Once we have this very hard function, we need to make it into a PRG, and Nissan and Wigderson's generator from their 94 result will help us construct this PRG. Now, all of this is happening in the classical realm. So what have we done? Well, essentially, we need to prove that it's secure against quantum computations. And for that, you need a construction that fits that condition. And that is the basic contribution of our work in the technical side. So once we have this PRG, the last step to put everything together is, unlike most things, we get a win-win argument here. If we assume that P space is easy, then I get a straightforward lower bound, which is implied from previous works from the classical realm. However, if P space is not in BQE, then essentially I mean that it's hard. So there exists a secure PRG by our assumption. And if I give this secure PRG to this quantum natural property, that guy's going to think that this is just a random function. So it's going to think that this is a very hard function. So think of an easy function as being something that's in the circuit class C, but a hard function is something that's outside of it, or it's random. So if you put all of these pieces together, essentially that will give us the proof of the theorem. Let's maybe get into some of the details. So what are these natural properties? So natural property was a concept introduced by Rasparov and Rorich in 1997, for which they won the Gödel Prize, I think 10 years later. So it is just a combinatorial property P. And the idea is that it should hold for a large class of all possible Boolean functions. The intuition here is, in some sense, again, to identify that a large fraction of possible Boolean functions may not have a certain structure that a very specific circuit class or a very small class of functions has, and the property is somehow an indicator of that fact. You want to be able to decide if this property can be decided efficiently, because you want to be able to use it in algorithms to make a decision. The largeness essentially implies, for instance, that with high probability, say at least half, any random function that you pick probably satisfies this property. And you want this property to be useful against, let's say, a circuit class, right? It's not enough that it's trivial to say something like, oh, the function just outputs a single bit. Now that's satisfied by all Boolean functions that we would care about. And in that case, you're not essentially learning anything new, or you can't use it effectively. So for the usefulness, what we say is that if F satisfies a property, then we can be sure that F is not contained in this circuit class C. So that's how you would measure its usefulness. For example, now, if I take a language in P space that satisfies this special natural property, then I can conclude that P space is not in the circuit class. So we have a separation. So what's a quantum natural property? Because we have promise classes here, we only get a promise property here. And it's again useful against some circuit class. And the best way to think about it as being a quantum algorithm that satisfies certain conditions. What are those? Well, it should be constructive. So if I'm given the truth table of a function, so this could be 2 to the n bit string. So the truth table of a function is given to this algorithm. It runs in time that's polynomial in the size of the truth table, but it can decide whether the function has the property or not. There is a certain density to this. So with high probability, at least half of the random functions can satisfy it. And if the function satisfies the property, then my algorithm will accept with very high probability. Similarly, we need it to be useful against C. So if my function actually falls in the circuit class, then I accept with very, very low probability. So that's how the learning property behaves. So how do we essentially use this? The lemma says that for some gamma, that is omega of 2 to the minus n over 2, if I have a learning algorithm that epsilon learns the circuit class in this amount of time, then there is a quantum natural property that is useful against the circuit class. How do you construct this? Well, the natural property is essentially an algorithm, right? So what is this algorithm going to do? It's going to use the learning algorithm A. And anytime A makes a query, it's going to use the truth table of F to answer those queries, because that's what it has access to. The algorithm outputs a hypothesis. And now I randomly pick T different inputs. And I run the hypothesis on each of these inputs. Because I have a description of the hypothesis, I can run it on different inputs. And I collect what their measured outputs are, V1 to Vt. And the output condition says that I output 0 if and only if this equation is satisfied. It's essentially telling me that if with a huge fraction of the BIs actually agree with f of xi, then I output 0, right? Which should be the case. If a huge fraction of the BIs agree with the function, then essentially it means that the hypothesis actually learned the function. And if that is the case, it is most probably easy, which means my learning algorithm, my natural property should output 0. So that is the thread that goes behind that. The proof sketch essentially beyond that intuition just shows that this can run in polynomial time. It's useful because the fact that A can learn all the functions in C means that this is a good approximation. Then by Chernoff bound, most probably this, with very high probability, this condition will be satisfied. And on the other side, when the function is actually random, then with just a counting argument about all kinds of hypotheses that the algorithm could output, we can show that a random function cannot be approximated well by hypotheses of this size. And that just goes by counting the number of functions that it could have an overlap with. And then using a Chernoff bound, we can show that this holds. So this is the first step to show that if you have a quantum learning algorithm, then you can get a natural property out of it. The second step is the conditional PRG. And the formal statement for that says that let's assume P space is hard for some sub-exponential time quantum time class. So 2 to the n to the gamma in this case. Then for some constant alpha and lambda, there is this uniform function family, which will be my generator family, such that the following conditions are satisfied. It stretches an L of n bit string into an M of n bit string. So L of n, think of it as being polynomial in n, and M of n is sub-exponential in n. So you take a polynomial amount of randomness, and you can hopefully stretch it out to sub-exponential. There is some uniformity constraint. Essentially, that just says that there is an efficient way to compute each of these generators given the input length. Specifically, it can be done in 2 to the L of n time. And finally, this has to be pseudorandom. So this large equation, all that it says is that given a random m-bit string and given the output of the generator, any circuit that is in Cm of n cannot distinguish between the two of them. So it cannot distinguish the output of the PRG from something that's truly random. So this is essentially what we get from the conditional PRG. I may not have time to go into the construction, so I will leave it at this here. And let's go to the third step. And if time permits, I can come back into the details of the construction itself. So now we need to do the third step, essentially to connect these natural properties and extract lower bounds out of it. So let's see what the formal statement for that is. We say that for every circuit class C, at least one of the following two conditions holds. For every Kn, there is some language L that is in the class BQE that cannot be computed by just generic Boolean circuits of size n to the K. Or the second case is that there is some constant nu such that if we have a natural property against this particular class, which is C and circuits of size n to the A, then I can say that exponential time, so this is deterministic exponential time, is not in the circuit class n to the A over nu. So there is some loss here, but yeah. So this is going to be the basis for the win-win argument that we want. So the idea for something like this is inspired by work by Oliveira and Santhanam, where they tried to do this in the classical realm and had lower bounds against BPE, so randomized exponential time. So the first of the win-win arguments kind of comes from their work, because essentially, let's assume that P space is easy. So this is the easy case. Then I can show that there exists some language LK that cannot be computed by Boolean circuits of size n to the K. This goes by some kind of a diagonalization argument, and I'm not going to go into the details because this is not exactly our contribution, but we kind of get it for free because this result was already known. The second part is what we would focus on, where in this case we say that P space is hard for sub-exponential quantum time. By our assumption, that gives us a secure PRG. And I also have an assumption that there is a natural property. So let's say that natural property is B. And what am I going to do with them? I'm going to explicitly construct a function Hn. I will have to show that Hn is actually computable in 2 to the O of n. Remember that the construction here is classical. So this function is also a classical function, which is why we can show that it's in deterministic exponential time. And finally, if my PRG is secure, then I can use that to prove that it does not have circuits that fall in this class. And that will complete the proof. To maybe go into a little bit more detail on how this argument works, here is how we use it. So our goal right now is to show that if I have a secure PRG and I have a natural property, then essentially this exponential time is not in this circuit class. So first thing, what we do is we look at these generators now, the output of these generators as truth tables of a function, right? So essentially for every W, you get an M of n bit string. So you can think of this now as being the truth table that is M of n bits long. Because the PRG we have assumed to be secure, technically there exists some W such that Gn of W cannot be distinguished from being random, because if that held, then you essentially have a distinguisher. And if it cannot be distinguished from being random, my natural property is going to accept it with high probability. Okay, so now we have to construct the language. Well, maybe what I want to do is, if there is some W like this, let me say that my language is the first such Gn of W, right? Because if it's random, then it's most probably outside of C, and I have the language that I want. But the problem is that it's not very easy to find out what this explicit first W is. And for our reduction to work, we want the language to be explicit. And essentially that happens because in the quantum case, we have only a promise property. So exactly calculating this probability is hard. And we don't have the time in sub-exponential time to do it. So let's change it a little bit. I convert the language now to be given by these tuple of strings, W and X, where W and X is in the language if and only if when W seeds the generator and you get Gn of W, the exit bit of this output string is 1. Or essentially it says that I have a generator that's seeded with W, and for the X input, I get the bit 1 out of it. Then if I collect all of these tuples, that is going to be my language. Now, the bottleneck to compute LG is just the same as the bottleneck to compute the generator's output itself. And we know that that is an exponential time, so that condition holds. Also now it kind of gets rid of this issue that I need to find a W for which this is hard, because somehow all possible W's and X's are included within the language. So how do we prove this? Well, there's a simple contradiction we can show. Let's assume that this language is actually within the circuit class, right? Then essentially it means that for every seed that you can think of, my generator can be computed within C. But that means my natural property has to reject anything that can be computed in C with high probability. And that contradicts with the previous assumption of the PRG being secure. So essentially this completes the proof. Now, how we get the parameters for the n to the a and n to the a over nu is just by being a little more careful about what is the size of the circuit to compute these things and so on. And so that just comes as an artifact of the technicality, and nothing more intuitive than that. So before maybe discussing the construction, are there any questions at this point? Okay. So I will try and give a brief overview of the construction in the time that we have, because I don't think I have time to go through all of it. So this is just a placeholder to remind us that when P space is not in sub-exponential time, quantum time, then we have a generator with the following stretch. It can be efficiently computed and it satisfies a pseudorandomness condition. So how does this actually work? So the first thing is I have to choose a P space complete function that satisfies certain conditions, which is downward and random self-reducible. So we want a PRG that is somehow secure against uniform computations. So think of self-reducibility as being a way to kind of get rid of any non-uniformity in the construction, and make sure that everything can be constructed in a uniform fashion. So we have to do this hardness amplification, and the construction itself is fairly straightforward. I take the function f and I take the k-fold composition of it. So now I'm acting on x1 to xk. Now the output here is going to be k bits long, but we want something that has a Boolean output. So we get back a Boolean function by using the construction of Goldreich and Levin, where you take a random k-bit string r and you take the inner product of fk of x with r. Finally, the last step is to use this function that we've constructed in the Nissan-Wigderson design. Now, all of this, as you can see, these are all just straightforward classical techniques, but we need to prove that this is quantum secure, and for that, what we need are things called reconstruction algorithms. What does that mean? Well, the construction, let's say, goes in a top-down approach where you layer it up at each step. A reconstruction algorithm is something that would go in, a bottom-up approach. And the intuition is that you want to use a reconstruction algorithm to generate some kind of a contradiction. What do you want to contradict? Recall that the assumption that we have is that P space is not in sub-exponential quantum time. So somehow what we want to use is, if there is a distinguisher for this PRG design, then I can reconstruct my algorithms and get a contradiction that P space is in fact contained in sub-exponential quantum time. And that is what we use. Okay. I'll try and go a little bit into the steps of the construction, and then we can see where probably I should stop. Naresh, is it correct that I have about 10 minutes to go?
Yes, Aarthi.
So the language just comes from the construction by Trevisan and Vadan. And the properties are that it's complete for P space with respect to deterministic reductions. It is downward self-reducible and random self-reducible. What does downward self-reducible mean? Essentially it says that if I want to construct an algorithm for input length n, as long as I have algorithms for smaller input sizes, which is like 1 to n minus 1, then there is a proper diagram, or there is a constructive way, a recipe that exists for me to construct the algorithm for input length n. So that's what downward self-reducible here means. That's how we use it. What random self-reducible means, it just says that if, let's say all I have is an algorithm that can solve the average case of a problem, I have a recipe to construct algorithms that can solve it for worst case inputs. So this is a very useful property that we will use. So let's maybe go to the first step of this construction, which was that hardness amplification part. Now the theorems that I'm giving here are the theorems for the reconstruction algorithms. So you will kind of see them going in the opposite direction of the flow of the construction itself. The first thing says that there exists some poly of n, k equals poly of n, such that if I take the k-fold composition of some function f, and I have an algorithm, a quantum circuit G, that can compute g of x equals fk of x with, this error, let's say 2 to the minus square root of n error, then there is a quantum circuit B, which has a polynomial overhead here in the size and in the error and so on, such that I can compute a single entry of this k-fold repetition, f of x, with error 1 minus 1 over poly n. So that is the reconstruction algorithm. For the sake of uniformity, I also want that there is some algorithm that, if I'm given this description of G, can construct this description of B efficiently and with small error. So this comes more because of the technical aspects. So like I said, going in the opposite direction, this helps me reconstruct from Fk, how do I get a circuit for F? The Goldreich-Levin part essentially says the following. I have a function F, and I have a quantum circuit A that does the following. If I take a k, x1 to xk, the vector of k inputs, and take a random string r, and I can output the inner product of f of x with r with high probability. So in this case, well, at least half plus gamma, then I can construct a quantum oracle circuit that helps me recover what f of x itself is with probability at least gamma cube over 2. And again, because we want the construction to be uniform, there is an efficient way to do this. And yeah, that's what the last line essentially says. So what does this prove? This helps us, given the Goldreich-Levin function f applied to fk, how do I reconstruct and get a circuit for fk? So this is that step of the reconstruction. And finally, we can talk about the Nissan-Wigderson generator. I will very quickly go through this. It's essentially some family S of sets S1 to ST. And each of these sets is of size n. They can take values from a universe of size m. And there are T of these sets. And what makes this the design essentially is that given any I and J, distinct I and J, the intersection between the elements is at most alpha. And that's the combinatorial design that exists. Nissan and Wigderson showed that there is some constant C greater than equal to 1, such that for any n and any t that is between n and 2 to the n, there exists such a combinatorial design. More importantly, we can construct any SI efficiently. How can we use this? Well, given such a combinatorial design and given my function f, which has some hardness conditions, my PRG is just going to be f, which is acting on, let's say, z restricted to the set S1. So what fz S1 here implies is that z is going to be an m-bit string, and I'm going to take n different indices out of that, and that's what my f is going to act on. And because this is a T design, there are T different elements here, and I will get a T bit output out of this. I hope that's clear, not too confusing. So this is essentially going to be my generator. So I will, all we have to say is now you can understand the maybe idea behind what this theorem is going to say. Essentially, this is going to tell me how I can reconstruct the Nissan-Wigderson idea from, let's say, and get it back to the Goldreich-Levin level. So you're reconstructing at a different level of the construction. And the proof maybe goes where there's not much intuition in the proof. It follows the classical idea. And the main idea is that there usually you think about the fact that you can, if you have a distinguisher, you can maybe guess some index I of the output. And our goal is to somehow sneak in this question X into that index I so that we can predict it with high probability. I'm rushing a bit here, but the way we would go back to reconstructing these things essentially is to start with the assumption that I have a sub-exponential time distinguisher, and I put all of these theorems together to kind of match up, to show you where it matches up with the construction, to get a circuit that on average can compute the f of x function with error 1 over poly of n. However, this can only do well on average. But we know that the language that we have is random self-reducible, which means we can change it to say that for every input that you give, I have a circuit that can output the correct answer with probability at least 2/3. We started with a sub-exponential time distinguisher. All the overheads are only polynomial overheads in this, which means you still get a sub-exponential time circuit for the language. And this is what gives you the contradiction. Essentially, this completes the whole roadmap of the proof. I'll just end with a few open questions, and yeah, any questions?
Are there any questions, or if there are no more questions, maybe we can end the call and thank Aarthi for her talk. Yeah.
Thanks everyone.
Okay, thanks Aarthi, thanks.
Yeah, it will.